Hi, welcome to our 11th lecture on topology. This is the third lecture on closed sets. Today we are going to talk about the class of closed sets. The class of closed sets is the counterpart of class of open sets. What is the class of open sets? It's a topology, right? So it's the counterpart. And by looking at the definition of, not the definition, but the properties of the closed sets, we will be led to a new notion called the closure of a set. These are the things which we are going to discuss today, and we also have to do something about uh, the adherent points in a metric space. Yeah, I think that's one class of metric space, one of our standard examples in our list, so we have to discuss that too. Okay, so we will do that also, right? I do not know which order I'm going to do. It all depends when I start. Okay, let's get started. Yeah. Okay, so let x d be a metric space, right? Suppose A is a non-empty equal. Assume non-empty is a subset of x and x is an adherent point, a point of A, right? We want to understand what is meant by that. Okay, so what are the typical open sets containing x? They are the form bxr, where r is positive. But again, we have seen the simplest open sets will be simplest basic open typical open sets will be bx 1 by n for n natural number, right? Yeah, so this is the collection of simplest open balls containing a given point x. Now since x is an adherent point of A, we know that A intersection bxn is not empty. Bx 1 by n is not empty, right? So that means there is a point common to that, and since the point it's a point of A, but then it also in bx 1 upon n, and the ball bx 1 upon n depends upon natural number n, so we will call it an. Okay, there exists an here, right? Therefore, what do you think I have got? For each n, I have an in A. That means I have sequence an in A. This is a sequence in an, right? I'm sure all of you know what is meant by sequence, so do not say that I have not yet defined, etc. Alright? Okay. Now, what is the distance between an and x? Remember, an belongs to x, the ball of bx 1 upon n, therefore this is less than 1 by n. So what does it say? Okay, if you remember your real analysis, or if you have done a little bit of metric spaces, you know the sequence an converges to x. Yeah, so what have we found? So what have we found is if x is an, what did I say there? Adherent point. Good. If x is an adherent point of A, then there exists a sequence an in A such that an converges to x. So what is the next question you can ask? So pause, review, proceed. So next question I can ask is the converse. Let x in x be such that there exists an a sequence in A such that an converges to x. Question is x an adherent point of A, right? So what does that mean? That means you are going to give me an open set U containing x, open neighborhood of x, and I want to show your intersection A is non-empty, right? Since you use open the metric space topology, that means there exists an R positive so that bxr is contained in U, right? If I show bxr intersection A is non-empty, I am through. Right? Because Bx or intersection A is contained in U intersection A. But this is very easy. Right? What do I know? I know that an converges to x. Right? That means there is a natural number n, so that for every n greater than or equal to capital N, an must be in Bxr. Right? Think of R as epsilon. Given epsilon positive, you want to say there is a natural number n, so that for all n greater than or equal to n, distance between a and x is less than epsilon. Right? So if I take my epsilon equal to r, right, for this epsilon there is a natural number, so that all my n's are going to be there. Therefore this is non-empty. Therefore for all n greater than or equal to capital N, an belong to Bxr intersection A, and therefore this is not empty. So we have proved it. So what have we proved? So this is the theorem we have proved. Okay, if you want to call it a theorem or a proposition or whatever, okay, x is an adherent point of A in a metric space XD if and only if there exists a sequence an in A, so that an converges to x. Okay, pause, review, proceed. Right? Okay. So just before I go further, let me just look at what have we done. Right? So in a given topological space X, we have defined what is meant by F. Okay, let's just let's just reformulate. Okay, the Lester lemma leaves a corollary. What is the corollary? Let XD be a metric space. A subset A of X is closed if and only if for every sequence an in A, so that an converges to X implies X is in A. Do you understand this? So I have A, okay, I have a sequence, okay, an, and if I know it converges to X, that X must be in A. This is my A. These are my ANs. Yeah. Is this obvious? If you remember, you understood the last lecture on closed sets, you know that, right? When is A is closed in a general topological space, A is closed if and only if in a topological space, if and only if A contains all its adherent points. Right? Now I want to know that A is closed in a metric space. Okay, that means I have to show. So now A is a subset of metric space XD. I want to know whether A is closed. That means let X be an adherent point of A. Since X is an adherent point, by the last lemma, there is a sequence an, so that an converges to X. Right? But what is our assumption about A? Yeah, you follow that. Therefore, sorry, A is an adherent point of A. Yeah, so by the last lemma, there is a sequence an such that an converges to X. Right? Therefore, X is in A. Are you following? Okay, maybe I didn't put it correctly. Okay, okay, just ignore. Okay, let us start again. Let A in XD be closed. What should I prove? If you give a sequence an which converges to X, and an is a sequence in A, then I want to know whether it implies X belongs to A. Do you want to accept it? Yeah, that's what the theorem said. the corollary. A is closed if and only if an. So if A is closed, I have to say if you give me a sequence an in A such that an converges to X, I have to prove X is in A. But then, since by the lemma, okay, this implies X is an adherent point of A. Yeah? But by yesterday's lecture, last lecture, we know, okay, implies if A, since A is closed, X must be in A. Because if A is closed, any adherent point must be an element of A. So we proved it. Have you understood? Please pause, review, proceed. So let's look at converse. Okay. So let A be such that for every sequence an such that an converges to X implies X is in A. Right? I am given a set A. What is the property? You give me a sequence an in A. Then what do I know? An converges to X. Suppose assume an converges to X. Then what I want to claim? X is always in A. Then what should I prove? I should prove that A is closed. So I have to check A is closed. Right? But that's very easy. To check A is closed, what should I do? A is closed if and only if every adherent point X of A, okay, if A is an adherent point, if X is an adherent point of A, then X belongs to A. This is last lecture. Right? Right. So let X be an adherent point. Point of A. Then by the lemma above, what do I know? There is a sequence an in A so that an converges to X. Yeah? Right. By the assumption on A, X must be in A. Yeah? Go back. What's the assumption? The assumption is this. Assume that any if I know the an is a sequence in A, so the an converges to X, X must be in A. With this assumption, A must be closed. Do you understand? So that's what we proved. So let me repeat what I said yesterday, because when I go through this kind of logical things, now I understand why many students find topology difficult. Yeah, that's because their logical thinking and staying focused is somewhat difficult. So my suggestion is, do not try to remember, recall or memorize these proofs. Just go through twice or thrice so that you get trained how to think logically. Then you will find it's easy. This is my sincere advice. I hope if you want, take it or leave it. Okay, now the last observation. Do you remember, if A is a subset of a metric space XD, we define dA of X. That was by definition GLB of dXA as A varies over capital A. And we proved this is continuous. In fact, we proved something stronger, but let's not worry about uniformly continuous or Lipschitz continuous in a metric space sense. But anyway, we know it's continuous, right? We have proved all those things. But what I want to know is, okay, when is dix is 0? Suppose dix is 0, that means what? 0 is the GLB, or if you prefer infimum, but I prefer GLB of this set, right? So if GLB 0 is the GLB, if I take 1 by n that is greater than 0, therefore 1 by n is not an upper bound of the set, right? If 1 by n is not an upper bound, that means there is an element of this set, namely dxa. So I have 0, I have 1 by n, therefore there exists one element of this set dxa which is strictly less than 1 by n. Since that a is going to depend upon 1 by n and hence n, I call it an. So there exists dx an in a, so that 0 less than or equal to dx an less than 1 by n. Right? Now do you see something interesting happening? By sandwich lemma of real analysis, this goes to 0, this goes to 0, that means this goes to 0, that means an converges to x. Yeah? If an converges to x, what does it mean? We had already seen it. If an converges to x and an is a sequence in a, what does that mean? That means x is an adherent point. See, these are the things usually in the topology courses not done. They only work with x and tau. Okay, so many times when you come to functional analysis or other parts of analysis where metric space is involved, students are always at a loss. They are not very sure of things. Please go through these things. As I said, do not worry about whether it's being taught or not taught, whether you would remember. Please go through the logical way of arriving at results. Try to think along with me so that thinking becomes part of you. It's a natural process, right? So what have we shown? If x di of x equal to 0 implies x is an adherent point. This is what we proved. Okay, pause, review, proceed. So what is the next question you should ask? Converse. So if x is an adherent point of a, does that imply distance between x and a is 0? This is almost trivial, all of you know. If x is an adherent point of a, in a metric space we know there is a sequence an in a. With what property? An converges to x. Right? You follow that? If an converges to x, this is if and only if distance between an and x goes to 0. You follow that? Yeah? So what does that mean? So what do I want to prove? Again, I will prove it because usually I know that infimum GLB analysis is always slightly tougher for students. I will go through this. So from this, I want to conclude the GLB of dxa a in a, that is nothing other than distance between x and a is 0. Okay, this is what I want to prove. Okay, let us go to the proof. So to prove GLB is 0, what should I do? So notice that each of these elements is greater than or equal to 0. Therefore 0 is a lower bound for this set. Okay, I will not keep saying, okay, lower bound for this particular set of real numbers dxa as a varies over a. Right? Okay. Now I want to say it's the greatest lower bound. That what does it mean? I have 0, and it's enough if we show give me any epsilon greater than 0, it's not an upper bound. Do you understand that? So to show 0 is the greatest lower bound, I have to show epsilon is not an upper bound. Lower bound for the set of real numbers. This set of real numbers. Right? But that's very easy. Why? Since I know an converges to x, okay, for this epsilon there is a natural number n, so that for all n greater than or equal to capital N, distance between an and x is less than epsilon. So in particular I have found one element of the set x, okay, that is strictly less than epsilon. Therefore epsilon is not a lower bound, but 0 is a lower bound. and any positive epsilon is not a lower bound. That means 0 is the greatest lower bound. Therefore dxa is 0. Do you believe me? Okay, unlike usual topology course, how many times I will bring in real analysis, least upper bound, JLB, LUB, etc. Yeah, infimum, supremum. So please review those things. I know real analysis teachers don't give so much attention to LUB, GLB. Okay, so let us conclude. So what is the conclusion? Okay, in a metric space, xd dxa is 0 if and only if x is an adherent point. Okay, this is what we have proved. Okay, pause, review, proceed. So in particular corollary, suppose A is a closed set in a metric space xd, then what do I know about dxa? And x is not, sorry, and yeah, and assume dxa is 0. Okay, let A be a closed set in xd. Okay, then I want to conclude, then what I wrote is correct. dxa is 0 if only if x is an adherent point of A. Since A is closed, if and only if x belongs to A, therefore x belongs to A. Do you see this? So if I have y not in A and A is closed, then distance between y is not in A. Distance between y and A must strictly be positive. Okay, you should understand these things. The simplest example is, let us take 0, 1 A. This is my y with the as a subset R with the usual metric topology, right? Then 1 is an adherent point of A, but distance between 1 and A is 0, right? Or if you want, let us say 0 and A, because let us look at 1 upon n, they are all in A, so they are an, and an converges to 0. You understand? But 0 is not an element of A. Okay, so distance between a point and a set can be 0 without the point being in the set. Yeah, so please review all these things. Go because I know for sure these things are not very much explained in this general topology course. Please review. So that more or less finishes what I wanted to say about adherent points in a metric space. Adherent points of a set in a metric space. That is done. Now we are going to the next topic. Okay, what is the next topic? So let X be a topological space. Do you see that my comma always comes to the wrong place? Yeah, it only shows I'm impatient. Yeah, right. Let C be the collection of all open sets. Class or collection of all closed sets. Okay, and this is in contrast with tau is a class of all open sets, but that's very something it's strange, because only I gave tau, after that I define what are meant by open set. Any element of tau is an open set, therefore this is not a very correct way of saying, but anyway. Okay, so these two are counterpart. Alright, now I want to understand the properties. Alright, think of it the way we define the class of open set in a metric space. Then we said that tau has the following properties, right? Similarly, now we have the collection C of closed sets in a general topological space. I want to look at the properties, right? Properties of C. So let's look at the empty set. We know that belongs to C, and X also belongs to C. Why? Because X complement is empty set and P complement is X, both are in tau, right? Therefore we know this. This is the first property. Second, okay, now what is the second property in tau for the topology? Arbitrary union of open sets. Okay, arbitrary union of sets in tau, that union also belong to tau, right? Now remember, what is a closed set? Complement and open set. Therefore what should be the natural thing for me to do? Should I worry about arbitrary union of closed sets or arbitrary union of open sets? Think. Because finally whatever I want to do should be deduced from the fact about tau. That is, arbitrary union of open sets is open, right? Do you understand what I am saying? Okay. So let AI be a collection of closed sets. Okay. Then I want to say intersection AI, I and I. Okay, that's I and I. Okay, again is in C. That is, arbitrary intersection of closed sets is closed. Okay. But in the case of topology, tau, arbitrary union of elements of tau, that union is still in tau. Whereas here, arbitrary intersection of elements in C, that intersection is in C. Right? So how do I know this is in C? That means I have to know whether it is closed. Well, how do I know it's closed? Only the way I know is whether its complement is open. Okay, this is a question I have to ask. Yeah, but that's very easy because we had already seen De Morgan's law. Says intersection of I in I, that complement is nothing other than union of AI complement I in I. Okay. Now do you realize why I asked you to watch my video on arbitrary union and intersection of family of subsets? Because this is again, okay, the teachers believe you had already learned set theory, but they don't understand you know only finite sets and finite collection of subsets. Okay, this kind of arbitrary collection, etc., you may not have learned, so it's better to learn them. Okay, this is another point which creates problem for students of topology. Okay, for basic set theory, and second thing is logic. Okay, so learn those things well. Okay, so all those things you would have learned well if you look at my foundations lectures. There are 4 lectures. Okay, please watch all these things so you'll become competent. Okay, now what do I know about AI? AIs are in C, that is if only AI's complement are in tau, right? For all I. Therefore these are all in tau. Therefore the union is in tau. Therefore this follows. And what should be the third condition? There what did we do? Take 2 open sets U and V, that is U and V elements of tau, then U intersection V is again tau, or finite collection U1, U2, Un in tau, then U1 intersection U2 intersection Un is in tau. So what should be the analog here? So let A1, AN be in C, then what should I know? A1 union A2 union AN is in C. That is a finite, take a finite collection of closed sets. Okay, the finite union of closed sets is again closed. Do you understand? So let us say as usual prove only for 2, let A and B be in C. Then I want to know whether A union B is in C. Yeah, but when does A union B is in C? I have to look at its complement. What is that? That is A complement intersection B complement. Now what do I know about this? This is an open set. This is also an open set. What is the property of tau? The topology, finite intersection of elements of tau is again an element of tau. This is the finite intersection, right? Therefore this is in tau. So this means is correct. Yeah. So pause, review, proceed. So what have we proved? If C is the collection of closed subsets of a topological space, then empty set and full space are in C, and take an arbitrary collection of closed sets, their intersection is in C, not union, intersection. And then take a finite collection of closed sets that the union is again closed. Right? Now just for 3 remarks on the condition 3. Okay. For example, let us look at Q. Okay, this is a set of R. Okay, with the usual topology or metric space topology, right? Now Q is a collection of what? Singleton X, where X is in Q. And what do we know each of singleton? These are all closed sets, right? Therefore Q is a union, arbitrary union of closed sets. In fact, a countable union of closed sets. But what do we know about Q? Q is neither open and nor closed. In particular, Q is not closed. Therefore 3 is not true in general for arbitrary union. Do you follow that? Therefore arbitrary union of closed sets need not be closed. Okay, right. So let us now come to the next thing. Now I am going to digress a bit. Okay, see, mathematics for me is a single subject. Okay, I don't think of it as algebra, analysis, group theory, ring theory, linear algebra, real analysis, measure theory, complex analysis, functional analysis, topology, points topology, algebraic topology, differential topology. See, all are parts of the same thing, right? And each is needed for mathematics to function well. Okay, so let us look at, suppose G is a group. Okay, you have defined subgroups, right? Then what did you observe? Intersection of subgroups is again a subgroup, right? And similarly, suppose V is a vector space. What should be the analog I should ask here? Suppose W is a vector subspace of V, then intersection of vector subspaces is again a vector subspace. And since you are all learning points to topology, I assume that you are all essentially MSc students, so you have learned ring theory. Okay, suppose R is a ring, you know what is meant by an ideal. Then what do you know? Intersection of ideals is again an ideal, right? Now what did we have? This I have not proved, but okay, so in some future lecture I will come to that. Okay, let's not forget it. I have to stick to this. Let X tau be a topological space. Then what did I say? Intersection of closed sets is again closed, right? So whenever such a thing happens, so just think abstractly. Mathematics is trying to see the pattern and abstracting, okay, as a meta result or a theorem. So I have some sets with the same structure, and the moment the intersection of such object with the same structure is again an object with the same structure, that is the intersection of subgroups is a subgroup, intersection of vector space is a vector subspace, intersection of ideals is an ideal, intersection of closed sets is a closed sets, intersection of topologies on a set is again a topology. I have not yet shown, but anyway. Okay, then there is always a natural question, okay, which mathematicians ask. Okay, so intersection of, okay, mathematical objects, mathematical structures of a particular kind. And equal to say a mathematical structure of the same kind. Do you understand this abstract result? All these four belong to this category. Then the question I ask is the following. Okay. For example, the group G, suppose A is a subset of G. Subset. Okay. Nothing to do. It's such a subset. Please remember, I am not talking about subgroup. Then I can ask, okay, does there exist a smallest subgroup H containing A? Right? In particular, you can ask when A is a singleton G. But let's not worry about it. Now, how do you answer? Notice that G is a subgroup and it contains always. Therefore, the collection H is a subgroup of G and A is a subgroup of H, is this collection is not empty collection. Therefore, each element here is a subgroup. Call this script H. Then let's look at H naught to be script H varying over script H. This intersection of subgroups, each of the subgroups contains A, right? Therefore, H naught is a subgroup, right? And that contains A because A is contained in each and every H here. You follow that? Now, H naught is the smallest subgroup. What do you mean by it's the smallest subgroup? If you give me H1 is a subgroup, so that A is contained in H1, then I want to know H0 is contained in H1. Right? Is that correct or not? That's correct, because H1 is a subgroup containing A, then H1 belong to this. One of the script H, right? This means H1 belongs to script H. Right? Therefore H0 is contained in H1. Do you understand? Yeah, please pause, review, proceed. The same thing is applicable to vector subspace, ideals, etc. So I am not going to discuss those things. But if you are interested in mathematics, learning mathematics thoroughly, please go through this argument again. Okay? So exercise. In the case of linear algebra, ring theory, that is ideals. Okay? Now I'll come back to our. So I have C. I know arbitrary intersection of closed sets is a family. Okay? This is again closed set. Okay? If I let us say C1 is a collection, then intersection of C, A and C1. Okay, this is again a closed set. This is what our condition 2 implied, right? So what is the question you can ask now? Can you think of the question? The question I can ask is, let X tau be a topological space. A is a subset of X. Does there exist a smallest what closed set? Okay. B said that, okay, B contains A. So what does it mean by smallest closed set? B must be a closed set among all closed sets that contain A, that is the smallest. That is, if you tell me C is a closed set and A is a subset of C, then what should be the relation between B and C? B must be contained in C. Right? Think of least upper bound, etc. The same thing. Do you understand this? So let us look at a collection CA to be the collection of all sets C in script C, such that A is a subset of C. That is, what is it? I look at all closed sets which contain A. Is this set non-empty? Of course non-empty, because X always there. Right? Do you see the pattern? Subgroups, ideal, vector subspace, okay, closed set. Everything is the same thing. The full set has to be an element there. Yeah. Therefore, what do I do? Now I look at intersection C and C in C of A. Okay, this will be a closed set. Okay, and that contains A because A is contained in each and every A, C, right? And it's the smallest closed set. Why it's the smallest closed set? If D is any closed set and A is contained in D, then D belongs to C of A. Therefore, D appears in one of the elements here. Therefore, so call this as B. Yeah. So B is the smallest closed set. Containing A. Yeah. So this B is usually denoted. Okay, it is denoted by one this is A closure. So if you want to be somewhat different, closure of A in the space X tau. If the topology is also clear, then you simply say closure of A in X. So any one of the notations. It all depends how much you want to concentrate. Okay, if X and tau are fixed, then I don't have to worry about it. I'll simply say A closure. Okay, sometimes it may be easier to use this notation. It is a closure of A in X. Okay, this is if X has different topologies, then I want to say closure of A in which topology. So I may have to write XA. Do you understand this? Right. Okay. So this is how we define the closure. Okay, it's called the closure, and it is called the closure of A in the space X tau or in X when the tau is clearly known. So we have proved the existence of a smallest closed set containing A and called it a closure. What do you think should be the question? Okay, for example, if you look at the first three examples which I gave, there are algebra examples. But usually in algebra, they may not have said what is the question. The question is, yes, now I know the existence of the smallest mathematical structure, okay, which contains a given set. The next question I would like to ask is, can you describe it concretely? Okay, the question is, can one give a concrete description of A closure? What does that mean? Concrete description. It only says if you give an element X in A when X belongs to A closure. Remember, A is always contained in A closure. Yeah, this is always true. Right? So I have to give, okay, characterize, okay, those X in X so that X belongs to A closure. That is, if I find the condition when an arbitrary element X is in the closure of A, then I have found out all the elements. Okay, all the elements of A closure. Do you understand? For example, just before ending the lecture, we will continue the lecture in the next class about this point. But let's go to group theory. And suppose my A is a singleton A, then I let H be the smallest subgroup containing A. Right? I want a concrete description. Okay, usually the teacher defines the subgroup, but I won't. Now I know the H belongs to that, therefore A belongs to H. Since H is a subgroup, A power n must be in H. For which n? For every n Z. You understand that? Therefore this set A power n has n varies over Z. This is contained in H. But a law of indices show A power n to A power m equal to A power n plus m, and A power n inverse is A power minus n. Therefore what do you show? This collection, call it H naught. H naught is already a subgroup. and that contains A. But H is the smallest subgroup, therefore we conclude H naught equal to H. That is, H is nothing other than A power n in Z. Okay. Do you remember your algebra teacher, group theory teacher always defined this and said this is a cyclic subgroup generated by A. Yeah? Right? It was thrust upon you. Now we arrived at it. Do you see the difference? Have fun. Okay? So let me stop. So in next lecture, we shall give a concrete description of A closure. Meanwhile, if you had understood the previous lecture, that is, okay, lecture 2 on closed sets, I think you can come up on your own what should be a closure. Try. Okay, and okay, let us see whether you are right tomorrow in the next lecture. Okay, have fun, take care, have a great day, we will meet again.